thank you everybody for coming. Today I'm very happy to have Dr. Spinelli joining us from Mitigation. So just to get all the things right, Marta got prepared in Paris at first in Marseille, and after that she moved to South Africa, where she worked with Mario Santos at Western Cape University. After which she moved to Trieste, where she worked with the supervisor of several of us at the Observatory. And since last year, she's a postdoc at ETH at the group with the group of Alexander Friger. Martin has worked on several very interesting topics in cosmology, and starting from CMB, so she was part of Planck of satellite and publications, and since then she moved to other photons with H1, and now she's the co-chair of the SKAO Cosmology Working Group. And has recently been involved in dealing with the foreground challenges and one of the first detections with MeerKAT cross correlations of H1 with MeerKAT telescope. And so today, Marta is going to tell us about the road to the SKA Observatory.
Thanks a lot. Yeah, thanks. Is it on? Yes. Thanks again for the invitation. It's very nice to be here, and I have friends around also. So the topic of the talk of today is only a partial thing of the thing that cosmology with the SKA can do. It's the subject we're most involved in, so I'm going to just talk about this as a preference. So the subject is 21 centimeter intensity mapping and how we can do intensity mapping with what we have now and what we have to prepare to actually do it with the SKA Observatory. So just a recap of why we are interested in 21 centimeter. What is 21 centimeters? So it's a line of hydrogen. So hydrogen is the main ingredient of all our research. And hydrogen is important from a cosmological perspective because it has played a role in across all the evolution of the universe. So from recombination, here is the CMB, and then during the dark ages, then when the first stars start to shine and the cosmic dawn start happening, and then all the epoch of reionization where the hydrogen got reionized, down to the role that hydrogen have in galaxy evolution as a fuel of star formation, and especially this part will be the subject of this talk. But the impressive thing about 21 centimeter cosmology is that you can cover really a large span, a really large epoch of the evolution of the universe. So in principle, you can go down to even the dark ages, maybe more realistic, the cosmic dawn. And the other important thing that I need to underline here is that you can do it with the SKAO. So the SKAO can really reach all these information about the evolution of the universe. So why that? Because the signal from the 21 centimeter emission get redshifted by the expansion of the universe down to all the radio frequency. So if you can cover the radio frequency, you can cover all the evolution from the cosmic dawn to the late universe. So the SKA Observatory is actually built in two pieces. One will be in Western Australia. It's called SKAO. It's done of around 500 of these stations with these 256 of these dual polarization antenna, and it will cover mostly this low frequency here. While the part that is built in South Africa, SKA Mid, will cover higher frequency, and so in our purposes a higher redshift. So of course the SKA Low covering all these frequencies doing a lot of other science. So here I'm really being biased and just showing you what for this frequency we are interested in. And the fact that, as we were saying, that the 21 centimeter signal get reshifted to this frequency. So if you can cover all this frequency, you can cover to cosmic dawn, to post-reionization universe. And in particular, of course, at this low frequency, you are covering the part more related to reionization. And if you want to work with SKA Mid, you can cover what you are interested in. So this part of the late evolution of the universe. In particular, let me underline that we already have some antennas. So this is a rendering, but these antenna here are actually there. This is the MeerKAT telescope. We already have 64 of these antennas, and it covers in a broad range of frequencies, so we can actually span from a 21 centimeter perspective up to redshift 1.5 in principle. So why this hydrogen is interesting from a cosmological point of view? I know these are things that you know, but it's always, I think, important to underline how much this mapping neutral hydrogen can give us information. So because from one side, we want to use neutral hydrogen in the late part of the evolution of the universe to understand something about dark matter. So how dark matter is distributed on large scales, how these evolve, and then maybe understanding something about the role of dark energy in all this. But the other side, we are actually measuring a bias tracer of this dark matter. So we are actually measuring the baryons. So we need to understand things about these baryons. And in particular, we, from a cosmological perspective, we need to know a lot of things like how baryon trace this dark matter. So what is the link between the galaxy and their dark matter halos, how these H1 galaxies are distributed in the large scales, and for example, how the H1 total density evolve with redshift, this kind of information. So there's really a lot of information and a lot of information how you have to connect the baryons and the dark matter. So how do we measure this large scale with distribution of neutral hydrogen? Well, we do something that is quite similar to what you do. Sorry about the coughing. I will cough a little bit, but no COVID. About the clustering, the same way you can trace the galaxies. So you can go and do a galaxy survey and do something like this. You can do the same with H1. It's a bit costly, and so you cannot go to really high redshift with that. So we changed completely the approach, and we say, okay, see, but we actually care about large scales for cosmology. So how we can do the large scales and don't have to resolve the single galaxy. So how we can then, with large scales, so we need to span large cosmological volume. So how we can do that? So the answer is this intensity mapping technique that is actually popular also in other lines, but here I will focus on the 21 centimeter line. So the idea is that instead of resolving the single galaxy, you have something, this large pixel in the sky. You have just low spatial resolution for these maps, and it looks a little bit like the CMB. So this is why some of the CMB technique can be reused also for 21 centimeter intensity mapping. Am I doing? Yes. So the other advantage of this type of technique is that all the things we said up to now, that there is a relation between at which frequency you observe and which redshift you are actually observing. This means that for the intensity mapping, what you can do tomography. So different frequency will be different redshift, and so you can reconstruct really a different redshift, how the distribution of hydrogen looks like. And so this gives you insight of how the hydrogen evolves, so how the last scale structure evolves. And because as we said up to now, you can really span a really large amount of redshift. So this is really proof that intensity mapping can be a really key cosmological probe. So this is in principle what we would like to measure, right? All in an ideal world, this distribution of hydrogen on large scales all around us, as for the CMB, but at different redshift, and learn a lot of interesting things. If we could do that, of course, you know, there is a lot of science you can take out of it. You can measure the power spectrum at different redshift. You can measure the BAO. Here is a plot from the SKA Red Book, and this is just for the BAO signal, but just I want to see that this pink line is intensity mapping against Euclid, for example. I'm sorry. And so, of course, maybe you cannot do as good as Euclid, but it's a completely complementary probe, and you can span a large amount of redshift. So it's really a lot of information here. And then you can go and when you have measured the power spectrum, go straight into the cosmological parameter. So since just to get a little bit more insight of what we can measure, for example, how this P21 looks like. So it's really similar to what you would measure for the galaxy, with the fact that it's intrinsically a redshift space distortion measurement, because you are talking about redshift. So you have your Kaiser term. This is the matter power spectrum that you want to measure. And then instead of having the galaxy bias, you have the H1 bias. So how is this relationship between the H1 and the dark matter that we were discussing before. And then since you actually measure temperature brightness, you have always to take into account the fact that you are not measuring exactly the H1 mass, but this emission in temperature of brightness that is connected also to the total amount of H1 that you have as a function of redshift. So there is a little bit of information you have to put also here. So as we were saying, this is an intrinsic redshift space probe. So for example, for doing forecast, you can go and look at the power spectrum multiples, so that you in general you take into account only the first two. And so this is what we did. This is a work that Maria here in the audience have led. with Matteo. And so we did some forecasts considering these first two expansion in multiples of the power spectrum and SKA mid-like observation. So we consider 6 bins of redshift. These are the different colors here. This is the monopole and the quadrupole. And then we consider SKA. I will go a bit more into detail about this. We have to measure this large sky to do this intensity mapping. We have to use a technique that is called single dish. So these 64 MeerKAT antennas are not actually used talking to each other, but as we had like 64 different antennas on the ground. So this is called single dish. And one of the things of this single dish is that you can reach large cosmological volume, but at the price of this resolution that we were saying. So this is why everything here gets killed, because the effect of the beam kills you a bit your signal. And then so here we put inside some expected noise, the SKA area that we expect for the SKA mid, and you can go and constrain some cosmological parameter. Of course, I mean, it's a probe that is a very interesting probe with a lot of potential, but of course it's not galaxy clustering, so it's always a bit less powerful than galaxy clustering. But the important is that completely complementary. And so here you see some constraint of the cosmological parameter with using the various multiple, and the information, take-home information is that you can get to a 10% error, more or less constraining power on the cosmological parameter. Then you can combine with Planck, for example, and see, okay, is this like an actual original probe that gives me more information? And the answer is, if everything goes well, yes. If everything is going well, you can go down to a factor, up to a factor 2 in improving the error bars. If you are a bit more pessimistic, you take into account the fact that maybe this temperature brightness that is related to the quantity of H1 as a function of redshift you don't know very well, that the bias you don't know very well, then you can kind of interpret these as uncertainties and marginalize overall these uncertainties. And being very pessimistic, you get to the orange contour here that you see are better than Planck, but of course not a factor 2. So it depends on how much you believe that other experiment can help you fixing this type of information in your data. But all the rest of the talk is going to be about the fact that when we try to measure the H1 in the sky, we don't actually see the H1, but we see what is the radio sky around us. It is mostly looking like this. For those who knows, this is the Aslan map scale, that the frequency that we are interested about. And you see that it's really, really high emission that completely, it's like a strong foreground with respect to the H1 emission. Of course, you can say, okay, maybe I can go and measure slightly patch in the sky where this emission from the galaxy is not so strong. Of course, you can do that. This is always a good approach. But then you have to remember that it's not only this emission from our galaxy in the radio, there's a lot of complex foregrounds there. So there will be extragalactic and galactic foreground, the free, the point sources. So it's going to be complicated. But it's not finished, because you are actually measuring things from a telescope that is even if it's in a remote area in the desert, in the 2 most remote countries that we have, still you have contamination from what is called RFI, that is a radio frequency interference. And this contamination means that you have to look at your data constantly and take out a lot of this data, because you think that these data are contaminated by stuff. So this reduces a lot the amount of data that you can have in a very weird way sometimes. So you have to be careful about it. And then of course you have a telescope, and as you know, in all the experiment, if you have a telescope, the telescope has an impact of how you take the measurement. And so you have to take these into account. This will be one subject that we will discuss a lot. And then, of course, there is a way you are actually looking at the sky with a certain scanning strategy, and this causes that the noise you are actually introducing in your measurement can be more or less difficult to understand. And so these are all the things that you have to actually take into account. Can we then what we know about this foreground? Maybe if we know something about this foreground, then we can try to understand how to deal with them. So this is just a plot to show you that the problem is quite big. So this black line here is your signal that you want to measure, and all these other lines here are different. Oh, sorry, I keep doing this. Are different type of this foreground emission, and you can see that they span a really large amount of scales with respect to the signal itself. So fortunately, one thing that we can use is the fact that in frequency, there is a completely different behavior of this foreground with respect to our signal. In particular, our signal is like really noise-like in a way in frequency, while we know that the synchrotron, the free are very smooth as they evolve with frequency. So this is something we would like to use. So to recap, the two key things are that, okay, these foregrounds are huge. They are there and much stronger than 21 centimeter signal, but they are also very smooth. So can these be used for our purpose? So the kind of the one of big question for our field is, can this property of the foreground can be used to separate the signal and the foreground? And the big other question is, yes, but when I add all these things that we have just discussed in the slide before, so the RFI, the contamination from the telescope, etc., can I still distinguish the foreground and the cosmological signal? Of course, this is our big question, because we need to solve this problem if we want to use this as a cosmological probe. So there are several techniques for those of you who, for example, works in EOR or are related to EOR stuff. Normally what you do in EOR is you use these properties of the foreground of being smooth, and you say, okay, if this foreground is smooth, they are super correlated, they will pile up in this low k-parallel mode. So it's all the same sentences. The foreground are smooth, they are at low k-parallel, and they are correlated in frequency. It means the same thing. It means the foreground will be lying around here. Then, of course, you have some contamination for the from the telescope, so you know that you are losing a bit more stuff here. But you try to do all your measurement in what you think it's a clean window for your signal. In at lower frequency, we don't do this a lot because we tend to lose too much structure if we do this. So there are other techniques that I will discuss in a second. Just to also give another idea of how people sometimes do it, this is an example from the cosmic tone, where you model the foreground with sort of polynomial, and you insert this polynomial behavior of your foreground in all your fit. So you hope that this is enough to describe your foreground. So this is, for example, another approach. So what I'm going to concentrate here is instead what we call separational cleaning, something that comes from the CMB and then has also been used actually in EOR. There are several techniques, the PCA, there are these KPCA, FastACA, GMCA, GPR. Now they are doing some machine learning enhanced GPR. So there are really a lot of techniques that you can use. But go for it. It's a measured property. So there's I mean, I'll go again on that. We have, but we know that more or less the scale is a power law, and this power law does not vary much. So that's why we kind of have measurements that confirm that. We know, for example, the free, we know that the free is super smooth. We know that the synchrotron, the spectral index is around minus 2.5 at low frequency, a bit more. But so it's a measured property of the foregrounds. For the foreground, yes, yeah, this is what normally when you look at point sources, they have, for example, also a spectral behavior similar to that. That's a good point. That's what we test with simulation. Yes, we this is something that we do a lot, trying to see if even in this type of situation, there will be we will be capable of separating the two. Because my point is that it's not only if the foreground itself has like this type of properties, that more or less we think that they don't. I mean, they should be quite smooth. So the problem will be that even if they are super smooth and you can totally believe that they like just a power law, then there will be all the fact that you have an instrument, that your instrument has a beam. And so there are really things that can happen on the line of sight in this way you were discussing. So this will complicate your cleaning, but still it works a little bit still. And we have a result. So when I show you the result, you'll get much more hype on this on this, because when I really tend to present the problem in the worst way possible, because I think we have to be open about the fact it's a difficult field, but it's working. So we have results, and I think it's worth pushing in this direction. So for example, I show you an example that works. This is exactly here for this. So because I arrive here and people say, yeah, but it will never work. So in a situation that is toy, but not so toy, because here the foreground are like realistical properties of the foreground. Most of these foreground are taken from, for example, the Planck sky model. So things that have been measured and then of course simulated on top of what you have measured. But so this is like a realistical foreground from the Planck sky model, scaled a bit at our frequency that is a bit lower. And then let's simulate, I don't know, 100 channel in frequency, so in redshift, around redshift 0.5. And we put a Gaussian beam and white noise. Okay, here we are a bit optimistic, but this is what people do a lot of times. And we say, okay, can we use this separation cleaning technique to then find the 21 centimeter signal? So the assumption is this, very similar to if people have seen some cleaning for the CMB case is exactly the same. So you assume that your cube of temperature is a sum of some foreground sources mixed with the matrix, plus some noise and your cosmological signal. And then the whole point is that how many of these sources I have. This is another subject of discussion, because this you have to actually understand with simulation, because or looking at the data. So there is not a definitive answer. In this case, it works quite well. You go and look at the eigenvalue of the frequency matrix. So you have this data cube and you construct a covariance matrix. You compute the eigenvalue. You look how this eigenvalue look like, and it will be something like that. So what you assume is that since the foreground is so much stronger than your signal, the first eigenvalue has to be the foreground. So at some point you say, okay, I assume that in the first eigenvalues, there are only contribution from the foregrounds. And then this will describe completely my foreground. All the rest is the 21 centimeter signal. So you do that. And for example, here you say, okay, here I'm already down. I stop at 3 sources. And I compute, I run principal component analysis like that. And these are the 3 sources that I extract. And then I look at how my components inside my cube look like. So the first one looks really like synchrotron. The second one looks a bit like free, plus these point sources that we put like a strong point source in the field to see how this was behaving. And so you see it's a bit of a combination of these two, but this is more or less describing the foregrounds that are inside my cube. And when I do the subtraction, so I take out all these 3 sources and their cover, and then mixing matrix from my total cube, I end up with something that is the signal plus the noise. This is the original, and this is what I get. So it works. It works quite well also for this type of simulation. So the whole point is, can we make this not work? And then when it doesn't work, can we solve it? This is all the purpose of this the work we are doing. So what is happening with data? Because now up to now it was just simulation. So here, remember to this we took out. You can take 3-4 sources out. This is what happens with the data. This is the real data from the Green Band telescope. This is a work that Laura Volz has done. Had been published this year. So this very colorful thing is first look just at the one with these crosses here. These are the H1 power spectrum measured after you have tried to subtract the foreground, taking up to like 36 of these foreground modes from your foreground. Because of course, the point is that when you have actual data, it's not only about which foreground you have inside, it's all these things about how the instrument and all the residuals enter in your measurement. So with data, you take out 36 components and you're still far away from the signal that is about here. So data are not doing great at the moment for autocorrelation because we still have to understand a lot of stuff. And here what you see is that, for example, if at least I try to cross-correlate 2 different seasons of data taking, so that you know that some of the systematics in 2 different seasons, this is what Planck also was doing, will be less. So if you cross-correlate 2 different seasons, there will be noise that these systematics that does not correlate, so they get killed in this cross-correlation. And at least you can go down a lot of even 2 orders of magnitude. Still, you are far from the signal. This is about here. So how do we exit from here? How it happens that we also with MeerKAT have detection? Well, because what you can do is to cross-correlate your cleaned map after these 36 modes are being removed with galaxy survey to check that you actually have some signal inside. And the signal is there. This is a detection of a cross-correlation power spectrum from Laura for cross-correlating with Wiggle Z galaxy and GBT clean data, and this distance from 0 is a detection of a cross-correlation power spectrum. So how would this happen? So the idea is that if you cross-correlate with something that has completely different systematic, of course, you kill all your systematic. So in more details with this slide, I steal from Steve Cunnington. Imagine you have your optical telescope and your radio telescope. So these will have a signal and a noise, and the signal and the noise. And so when you do your autocorrelation of your signal, you will get all these this noise term, and this one will go away because they are not correlated. And so this is the signal you want, this is the noise you don't want, and also the same one for the radio. So when you do the cross correlation, these noise terms get suppressed by the fact that there is no correlation between the noise in the galaxies and the noise in the H1. And so there is really a good amount of information that you can extract if you do cross correlation. And this is a nice cartoon that he did that demonstrates that there is all the bad things that goes away and all the good things that get enhanced in the cross correlation. So let me go to our data and show the fact that we also can do this. Just a little bit of technicalities that I really always love. This is the MeerKAT telescope. This is the real one, a photo taken from the Karoo. So there are already 64 dishes there. So we have taken data with all the 64 dishes. We have a survey that is called MeerKAT. I'm going to show the result in a second. So again, the technique is called single dish, meaning that we don't look at it as an interferometer, but we need, because we don't have the distance between the interferometer to resolve the scales that we are interested in for cosmology. So we just use this in single dish. But it enhances a lot the signal to noise because you have 60, and then you can look at systematics because you have 64 measurements of the same thing at the same time. So again, we did something similar to what the GBT team has done, and we targeted Wiggle Z 11-hour field so that we knew that we could at least use cross correlation. So the way that this fast scan of the sky to go to the large scales is done is with these telescopes that are at fixed elevation. So elevation is kept fixed, and then they scan like that. This is very important for us because the pickup from the ground can be important. So if you stay at the same elevation, you are sure that you are not doing something wrong with that. This is how it looks in the sky when you look at it in right deck. So I'll show you this because you'll see a bit of maps like that. So if you're asking yourself, what are these strange fringes, is because the way we take a measurement in the sky creates this pattern in the sky. So these are our observation. This is a successfully calibrated block of data. This is just one frequency. So the survey is called MeerKAT, and Mario Santos is the PI. So as I was saying, again, single dish mode. This is a very nice paper from Jingjin Wang that we wrote last year. So this paper demonstrates all the calibration pipeline. I'm not going to enter in the details for that, but this is our final data. So you can see that there is a smooth emission, that is the synchrotron emission mainly that we were discussing before. And you can recognize that there are also clearly the point sources. Here they are highlighted in magenta, so you can actually see them. So when we try to do the cleaning, you do exactly as before. You do this PCA machinery, and you take out 30 of these modes, hoping that you are killing the systematics, and you end up with this. And if you do the power spectrum with this, you see that you're still out with respect to what you would like to go. But as before, as you cross correlate with galaxy survey, in particular here again Wiggle Z, because we are in the same field in the sky, you get a power spectrum detection, and actually a very good power spectrum detection. This is a 7.7 sigma detection of the cross correlation power spectrum. So this is a very good result. It means that beside all these things, these systematics that we see here, there is an H1 signal behind, and this is like really important also because you can use this detection to say something about how, for example, the omega H1 evolve with redshift, the redshift that we have measured, or the bias, for example. Questions? No. all the Wiggle Z galaxies. Sorry about that. So just to recap a little bit where we are and what we want to do. So what we have is this 21 centimeter intensity mapping data that we admit are difficult to clean, but we have a cross correlation signal. We have simulation that you have seen, they are not as precise as the data. They don't have all the complexity of the data. And then we have all these cleaning methods that they work very well in simulation, and they work-ish in cross correlation for the real data, but still we kind of never tested these foreground cleaning methods on difficult realistic simulation. What then we would like, of course, we need more and better data, because the more data, the better the data. Also, this problem of cleaning the foreground and all the systematics will go down. And then, of course, we need to work on more realistic simulation, more sophisticated cleaning methods. So we need all this. So if you want to be prepared to the SKA, there is stuff to do, but I mean, we are working hard, and there is a lot of already, I think, interesting things that have come up in the community in the last years. The final aim, as we were saying, sorry, is this 21 centimeter power spectrum that we would like to detect, not only, but to be sure that we have detected something, because this process of cleaning, you need to control if you are also cleaning the signal. So there is a lot of work in simulation. This work is called the transfer function problem that you have to take care. So simulation are super important to validate your findings. Okay, so let me just now quickly go through some ingredients that we need for the simulation to improve and what we have done, and a bit what we are working on from the simulation point of view. Of course, we are working hard on the data. We are trying to understand what we see. We have new data, and but I will spare you all the nitty-gritty details about the data and discuss more about the simulation side. So first of all, of course, if you want to be credible cleaning, you need also to mock the 21 centimeter signal maps to put in your simulation. So there are several ways of doing this. The way we have used in some of our works is starting from getting some key ingredients of how the H1 evolves and how it plays a role in galaxy evolution using a semi-analytical model. You can use whatever semi-analytical model. In particular, since I was in Trieste, we were using the one from Gabriella De Lucia, this is called Gaia. And for those, I think here there are somebody that works on simulation, so maybe you are familiar with that. But the way a semi-analytical model works is that it reads through the galaxy merger tree of an embodied simulation and paints properties of galaxy that evolves and the way this merger tree evolves. So one of the properties that you can trace in this simulation that Gabriella and collaborators have done is the H1. And so, for example, you can estimate what is called the MH1M halo relation that relates the total quantity of H1 as a function of halo mass. There are different models from that. There are also work that Andre here has done. This is all simulation. This is Andre. These are all simulation or model fitted on data, and this is the result from the semi-analytical model that is just with these details that especially a low redshift AGN feedback seems to be important. So here you would expect the thing to be quite straight as there was supposed before, but then you actually see that there is a bit of eating coming from the AGN feedback. So this is very important to compute this type of relation, to have model for this, because if you want to do fast simulation for your purposes that are not now necessary subtleties of baryon physics, if you want to generate this fast map and big maps, especially because you want to cover the full sky, you can use this inferred from simulation MH1M halo relation and paint it on halo catalog. If you want even like a fast halo catalog, in particular here we have used Pinocchio to generate this stuff, and so this is how you get your maps. Okay. So for the foregrounds, this is what I was saying before. This is, for example, how the beta, so the scaling, the spectral index of the synchrotron looks like taken from some Planck sky model fitted stuff. So this is again what we are seeing, the Hazelham map, and then you have the free, and for example, the free, you know, it's quite of galactic origin. So if you stay far from the galaxy, it's not one of the most problematic. Point sources can be quite problematic if you have strong point sources in your field, and so this is one of the things that we, for example, worked a lot to try to simulate it at best, to use like realistical modeling. Okay, now I know that for the theoretician, these are the boring part, but this is kind of my daily work is trying to understand this instrumental effect. So I'm gonna get a little bit into this now. There are several things that we need to take into account if we want to understand the data, and at the same time to actually do some simulation that looks like the data, that are reasonable. So, for example, for a long time, we have used this Gaussian beam. So this is the beam is the way the telescope reacts, the way the telescope sees the sky. So normally you can say, okay, my telescope just sees very well here, and then it goes down as a Gaussian. So in reality, with the dish that we have with MeerKAT, it's not the case, because what is happening is that there are these things that come up again that are called the side lobes. So these side lobes interact, for example, with the point source, interact with the structure of the synchrotron, and we really need to take this into account. The other thing is that the scanning strategy, this peculiar scanning strategy, can generate, now that we don't have a lot of signal to noise, strange patterns. So we have to be really important. It's really important that we understand them, and also if you have like asymmetries in the beam, this can cause other problems. There's one that I will not discuss, but for example, this horrible problem of the polarization leakage. And the last but not least, as we were mentioning before, so this is in our frequency range. This is like a raw observation, not calibrated, not nothing, just the raw signal. And this is what you see. So these peaks are all this RFI contamination, and all this part you have to take out. And this part that looks cleaner, the one that we use, are actually, if you go on a smaller scale, full of these things. These are mostly satellites, so you have to be careful on that. Okay. So yeah, I'll may speed a bit, also because maybe this is just things that I like. So if we put these side lobes in simulation, so you can do this fancy plot regarding how the beam evolved with frequency, you get a problem. So this is what you would like to reconstruct. And all these lines here just tells you that if you have side lobes, and if your frequency dependence of how the beam evolve in frequency is the one that we have measured up to now in MeerKAT, really the people that works on the telescope, you may have problems because the cleaning gets confused by these rippling plus side lobes and gives you a residual or too much to clean systematics exactly similarly to the BAO scale. So this is something that we really need to understand. So with all these things that we have improved in the years about the simulation, we decided last year to do a foreground challenge just to test a little bit. These are things that in general are common for this type of fields. So we put together, these are the people that participated. This is a part of the SKA intensive mapping focus group. So we worked like almost 2 years on that. So we put together various data cubes with increasingly level of systematics inside, try to be as realistic as possible. And we did a blind challenge. So we give it to people that were like expert in these foreground cleaning methods and say, okay, can you give me back what you think is the level of the signal? And so we see if you're getting right. Because remember, up to now, the simulation were working too well. So what we see is that there are, this is, for example, the result on the cleaning quality. What you have to see here is just that if it's not white, it means that they didn't get it very in the right way. And you can see that there can be problems at low frequency. There is this pattern here coming from these strange side lobes, but more or less, in a lot of scales, you are around the 10–20% in the recovering of the signal. So we can do better with the simulation to challenge even more people. And so we did this paper where there are these nice plots that kind of gives you visually how much the different foreground methods behaves. So the idea is that the more the spider plots is, the more they are extended in the in the circle, the better it is. So for example, this method behaves very well on some criteria and much less in this other, for example. So you can compare and try to understand stuff. I'm almost done. So what we need to move forward? To move forward, we need a lot of stuff. Of course, we need data. We have data. The first detection was done with only 7 blocks of data, meaning around 10 hours of data. Now we have 41 blocks that we are analyzing, and a slightly bigger patch in the sky. We also have what is called UHF band. UHF band is, so these data up to here are what is called L band for MeerKAT. That is, let's say for us around redshift 0.3. And UHF band, you can push it a bit to higher redshift. So for us, it's interesting because you can go to higher redshift. At the other side, we are trying to do the simulation and try to put all the, understand things from the data, I put them in the simulation and see if the foreground cleaning still clean them. So of course, again, we would like really to measure this 21 centimeter out of our spectrum because it contains a lot of information for cosmology. So then, in the end, I rushed it a little bit. So I arrived to my conclusion. So I hope I convince you that 21 centimeter cosmology still have to prove its full potential, but offers really an incredible amount of information for cosmology, for the evolution of the universe. A lot of redshift are covered. Intensive mapping surveys are there. These are the ones that I discussed. I discussed just mostly MeerKAT and GBT, but there are others, and people are working hard on these and taking data and try to understand what is going on. There's also new fancy instruments that are planned, especially in the US, not only the SKA. So we have a detection in cross correlation. Other people have it. This is true, but this is the first one done with the single dish composing these the various MeerKAT dishes. So it's a new thing. It's important. We are analyzing this new data, and we are really doing an effort in understanding the instrument again more in details and try to also improve the analysis pipeline. Of course, at the other side, while you understand more on the data, you have to keep really improving this simulation. And of course, I just mentioned some very basic thing to simulate the 21 centimeter maps, but especially when you do cross correlation, and you cross correlate with different population of galaxy, because here I show Wiggle Z, but if you cross correlate with BOSS, you can have a different type of galaxy. So you want to have simulation that includes also galaxy properties, so you can say something about your cross correlation power spectrum. So the idea is that there is a lot of people working hard for this, but of course, if people are interested, there's always space. And so what we are trying to do is really to prepare for this SKAO era, and the fact that this intensive mapping could contribute to our knowledge of the large scale structure. And I finish here. Thanks a lot.